Good evening to judges and all present here. This topic deals with optimization process in tire design. Here, with the help of optimization process, I am going to show the attempt to reduce tire noise. C8 is a part of RPG group, and we are one of the flagship company of the RPG group. This is the journey of C8. We are the largest tire exporter from India. So, tire noise generation has various mechanisms. This stick slip, when tire comes into contact, several points wants to come into contact, and several points which are already in contact wants to come out of the contact. So this consistent coming out of contact and coming into the contact generates a particular noise. And adhesion stick snap. So when a particular tread part wants to lose the road contact, the adhesion forces tries to bring it back to contact. This also causes a noise. Whenever tire rolls over an obstacle, it causes radial force variation. That is a vibration and hence the noise. When a tread pattern comes into road contact, the voids and grooves try to suck air inside. Similarly, when it leaves the road contact, this sucked air will be pumped out. So this air sucking in and pumping out will also cause noise, that is air pumping noise. This noise generated will be enhanced by some mechanism. Those are nothing but resonance. So this will enhance the noise. So this every noise generation mechanism generated a noise of particular frequency, and these frequencies are determined by the frequency of distribution of pitches. Because noise generation has two components. One is tire speed, rolling speed, and another is frequency of distribution of these elements. So tire speed is a user's input, we can't control it, so we will try to optimize the pattern's distribution. So the amplitude and frequency of emitted noise will depend on the particular arrangement. So like a tire is a rotating body, so basic mechanism in a rotating body is if the objects are equally spaced, then the frequency of noise generated will be equal to the number of objects. Like here, there are 10 equally spaced elements. So basic natural frequency will be 10. If like revolution per second is 1, the noise will be 10 hertz. Similarly, if it is like 50, noise will be 500 hertz. So it's basically RPS multiplied by natural frequency. And in these kind of cases, noise is called tonal noise, because entire acoustic energy is distributed at some particular peaks. In this spectrum, we will see only peaks. So these are called tonal noise, and these are very disturbing. I have some particular cases, like there is a noise of 500 hertz. Sound is not coming. Okay, anyway, like I had some example. Okay, so I had some examples so to show how disturbing this may be. Okay, so like this tonal noise of 1000 hertz, like this tonal noise of 1500 hertz. These are very disturbing. So objective should be distribute this noise to entire spectrum, so that like it should be a broadband, so that every frequency should come into the picture. So our objective is tire noise reduction. Again, make it somewhat pleasant. It can't be pleasant, make it somewhat pleasant. So tire noise is highly influenced by the tread pattern design and the arrangement of pitches. An optimized pitch arrangement reduces this noise emission. So in practical cases, like these elements highlighted in red boxes are not of equal sizes. Because if these are equal sizes, that will be an identical arrangement. So these are of of unequal sizes, so that like this is a case where equal or every pitch is equal size. This is a particular single pitch. If I rotate it, it will become full tire, and typical noise will be similar like tonal noise for a particular of having a particular frequency. So if I have a thread pattern where different types are used, so that the resulting frequency will be distributed. So here, this noise, we could say it's a broadband. So this is a comparison between a broadband and a tonal noise. Here we could say like in tonal noise, the maximum amplitude is somewhat 65. That is equal to number of total pitches. While in broadband, it is somewhat near 45. So it's a huge like reduction. 36.5 and 65, okay. So our aim is to have a particular arrangement where we could get even lower noise, lower noise. So it's like we are translating this problem into an optimization case. Like this is a noise spectrum for a particular sequence. This is for another sequence, and this is comparison. So here we are finding that a blue pattern is showing less lofty peaks. So this is a wanted one. So even in unequal distribution, two arrangements are giving different noise. So how to find the required arrangement, pitch arrangement? So here, noise emission converted into the pitch sequence optimization. There are many optimization engines available. Some are user-defined, some are inbuilt in HyperStudy. So we found genetic algorithm is the best in this case, because literature also supports this. So like genetic algorithm is nothing but like nature's evolution process. It mimics the Darwin's principle. It basically operates by two operators like crossover and mutation, distributing over other frequencies so that tonicity will be reduced. Our optimization engine was GA. It was a collaborative optimization where solver and optimization engine were interacting with each other. So our solver was hypermath. How to calculate for a particular pitch arrangement, how to calculate the maximum noise index. So for this, I have written a code in hypermath. My solver was hypermath, and GA was used from HyperStudy toolbox. So this was noise signal from a single pitch. It's in time domain. We did FFT in hypermath. And in frequency domain, this was the frequency. So these are the other tire parameters, design parameters. These were our variables. What should be the sizes of each pitch, and what should be its position with respect to the other pitches? That is basically sequence arrangement. So this is like methodology. We distributed several numbers to each pitches, and these were basically our design variables. So A will be the first pitch, B will be the second pitch. These are our design variables. And this is a glimpse of our hypermath code to execute the solver part. This is hyper optimization setup in HyperStudy. Like there were typically 67 pitches, total number of thread pattern units around the tire. And this was the convergence story, convergence history. So like the existing sequence and optimized sequence were compared, and optimized were lower one. So benefit was like optimized pitch sequence reduces the noise strength. Hypermath provides a powerful code writing platform. It was very easier for us to write a program. Earlier, the entire study was done with the help of an external agency, and it was taking 1 month and $400. Now it's a work of 1 day, an in-house developed code. Earlier, we were doing this because of ignorance or because of not exploring this area. We were doing it with the help of some external agency, not even in India. So now this is a very handy tool. Finally, I would like to thank C8 management and Altair for this support. Thank you.
optimize for that, the shared location or the dimension, right? Other than, so what are all the other parameters? Because from the noise perspective, the pressure, the kind of road, so where are those inputs that you have considered?
Thing is that, sir, whatever with the
Or is this for the only one type of, and then you just optimize them?
These all generation mechanisms are governed by this sequence. Everyone, like amplitude part, air pressure, like mode shape, and everything. But every mechanism has contribution from trade pattern. So whatever will be like sidewall vibration or wilt vibration, so that will have some, the source is from, the vibrating source will be from tire. So whatever will be the mechanism, whatever will be, the input's frequency will be that of the trade pattern frequency. So entire noise will be governed by this. So like if you want to go like what will be the noise dB value at particular distance, yes, we need to consider other things, yes. But this is the thing, this will determine the entire phenomena. For each phenomena, we have a particular testing method and particular simulation method. But everyone will have content from this pitch sequence, because source, vibrating source is coming from tire only, from road only, and pattern is only in contact with. So its fundamental frequency will be an inherent part of the spectrum, noise spectrum. That's why our aim was to optimize it. Yes, of course, what you said, there are various mechanisms. Yes, sir.
What is the percentage level that you have achieved actually?
Yes, sir. It was 28, and we got to 25.5. So its amplitude, if you go to noise level, it will be squared and the logarithm. So that will be reduction in dB value. So from 28, we got to 25. Even some encouraging values are also coming out.
Yes, so for the existing sequence and the optimized sequence, there is no much difference actually.
Pardon, sir?
The existing and the optimized sequence.
Yes.
There's no major significant difference.
Like peaks are reducing. Optimized is in red one.
Yeah.
Okay, these are on x-axis, these are harmonic numbers. These are frequency basically. If you multiply this with revolution per second, that will become frequency.
Okay.
So sequence is different things, sir.
Okay.
Okay, thank you.
Amplitude from first harmonic to second harmonic. Like that 130 which is coming to 25, it is it won't be so much unpleasant what it is at around 70.
So thing is that like you shift your peaks to the right hand side of the spectrum so that it is like
That was your target
yeah,
actually.
more pleasant. Okay, thank you.